Right. Good morning, good afternoon, good whatever, wherever you are. My name's Cameron. I am the content lead at Tinybird. Got Alistair here with me as well. And today we're going to build some real-time analytics APIs over Kafka. So what we're going to do really quick is just kind of do a little intro. I promise we won't pitch Tinybird. We're going to get into this demo really fast. But before we do that, just a couple of, not ground rules, but things. If you want to ask questions, you can do that in the YouTube chat, and we'll kind of answer them as they come up, or at the end, if it makes sense, we'll just kind of keep an eye on those. And then, of course, you can always email us if you have questions or want to follow up. You'll get a follow-up email after this that has the recording, as well as the GitHub repository of the code that we're showing today. So don't worry about taking notes or anything. You'll have the whole GitHub repo. Yeah, let's jump in. Um, so before we kind of do the demo, I want to explain one thing real quick, which is what do we mean by real-time analytics? We're building real-time analytics APIs today. So what exactly do we mean by that? So kind of real time, when we talk about real time, we talk about two qualities, which is freshness and latency. And by freshness, really what we mean is, how soon before data is produced is it available to be consumed or queried? I like to think of it in terms of SQL. It's like the difference between if you said, select now minus the timestamp of the data, that's how you would measure freshness. And then latency is query latency, and so when I make a request to a source of data, and I want to run some analytics on that, how quickly is that going to respond? And in real time, we expect freshness to be in a matter of seconds, single digit seconds, and then latency we expect to be in milliseconds, and ideally less than 100 milliseconds. Um, we add a couple things when we start talking about analytics, which is, of course, this query complexity. So we're doing complex things like filters, aggregations, joins, windows. We're not just doing very basic SQL. We're trying to do much more complex queries, and then we're also querying not only over just streaming data over sort of small bounded time windows, but we actually want to be able to incorporate historical data into that as well. And so that adds kind of an extra level of complexity over something like stream processing. And then the last thing is concurrency. So especially with Tinybird, what a lot of our customers are building user-facing applications, and so we need to build APIs that can respond to many numerous requests, maybe thousands of requests per second, as we have many concurrent users accessing these APIs. So when we talk about real-time analytics at scale, building APIs for those use cases, these are the 5 tenets that we really focus on. So with that, kind of let's talk about what we're going to build today. So the idea here is this is really like a last mile logistics problem. And what we're going to do is we're going to get a stream of IoT data from a fleet of scooters in Las Vegas. We chose Las Vegas because a lot of our team were at reInvent. I guess it was last week, 2 weeks ago. I don't remember. Time flies. And a lot of what we're going to show today, everything we've set up is on AWS. So we figured a little nod to reInvent there. We're going to have kind of a user location and an app, and then we'll have some scooter data and some pricing data. You'll kind of see how that works. You can see the tools that we're using today. We're going to use Confluent's version of Kafka for streaming. Uh, Confluent is a very, very easy, very fast way to scale up with Kafka without having to worry about infrastructure. We've got some scooter dimensions stored in an S3 bucket. We'll ingest those into Tinybird. So both Confluent and S3 will go into Tinybird, and then we're going to use Retool for application development because it's really easy. And so our goals are really to build this kind of pseudo scooter app where a user can see the nearest scooters, get a dynamic price based on maybe the distance of the scooter or how many are available. And then if we get to it, we might do kind of a business view, things where a business could maybe like change pricing, add a surge pricing, something like that. And then also monitor the status of their fleet. We may not get to that. That'll kind of be just for fun. And then kind of as we do this, well, actually, let me just show just so everybody kind of has the idea here that this is the basic data flow. So we're using Alistair's written a nice little Python script to generate some pseudo scooter data, and that's streaming into a Confluent topic. And then we're going to join that scooter dimensions in S3, do that Confluent topic in Tinybird, and then build this user-facing app in Retool. And then if we get to it, that little gray line is kind of showing like that the business could use some controls maybe to change the pricing that the user sees. We'll see if we get there. As we jump into this, we're going to have a little fun and sort of kind of imagine, because Tinybird's a really collaborative tool, and it's really common to have, software developers and data engineers working together. So, I'm going to kind of play the part of the full stack dev or kind of the back end dev. Retool might make me look like a front end dev, but I'm not. And then, Alistair will kind of play the role of the data engineer, really focused on optimization and making sure that we're building an optimized and a high quality data pipeline. So with that, I'm going to hand it over to Al to get us started on this demo.
Yeah. So,
Alistair, I think you're muted.
Am I muted?
No.
Yeah.
Hear you.
You can't hear me.
Being fun. All right. Nothing?
Nothing.
Oh, try again. Oh, shoot.
Can you hear me?
I had my speakers muted. I'm sorry. Okay.
Well, that's a nice.
Everybody can hear you but me. Okay. Yeah. Okay. Go for it.
So before we started this, somebody let me know that I think Vegas doesn't actually have scooters. So we might be breaking
now.
new ground here. We also had a question in chat, which was Confluent. Somebody asking if Confluent is managed Kafka. Yes. So Confluent Cloud, which is what we'll be using, is a entirely cloud-based serverless Kafka. So you can go in, create an account, hit a button, get a infinitely scalable Kafka cluster. Works just like normal Kafka, but you don't have to deal with any of the installation and management and all that kind of stuff. So we won't be showing too much of that. We've already pre-created a Confluent cloud cluster in AWS, and we'll just be integrating that with Tinybird. So that leads me
and I will just add real quick is that you can also, Tinybird integrates if you are hosting or managing your own Kafka cluster. That's also a native connector in Tinybird. So we support lots of various flavors of Kafka.
Yeah, pretty much anything that speaks the Kafka protocol, even if it is not actually Kafka. But we're going to go with Confluent because, hey, we don't want to deal with any of that today. Great. Nice segue into what I'm actually going to do, which is integrate it. So this is that you can see on the screen at the moment is a Tinybird workspace. It's a blank, empty one. So if you want to go and see this yourself, you can go to tinybird.co, create a free account, no credit card. You'll get into our free tier. So there's no time limit. You can build along with us, try out the product as much as you want. So I'm going to start by adding a data source, and that's how we connect our external systems to start bringing data in. So I'm going to click that, and you'll see that these are a bunch of managed connectors that we've got. And so we host and manage all of this for you. So you don't actually need to have like external ETL tools or scripts that bring your data in. We manage this stuff for you. So I'm going to go ahead and pick the Confluent one because we're going to integrate Confluent. And that's going to give me all the connection details I need to add. So I'm going to start with our Bootstrap servers, just as you would with any Kafka, which is here. So you can see that we're on US East 1 in AWS, which is the same region Tinybird's in. So we're using our new AWS US East Tinybird public region. And I'm just going to call this Confluent. And then I'm going to use my key and secret, which is going to auth me. And if I hit next, that's going to connect. So we're now a just normal Kafka consumer. And you can start to see the topics that we've got. So we've got one pre-created topic, and they're called scooter telemetry. And I'm going to hit next. And I'm going to start from the earliest. And that's just picking your offset to start with. And that's going to start importing the data that we've already got in that topic. And actually, that has reminded me I need to start the data generator. So we've got fresh new data coming in. So I'll just kick that off, and that's going. So this is Kafka topic has got some legacy data in that we've already put in, and we are now streaming in fresh data. We're generating we're pretending we have 5,000 unique scooters in there. And so we're generating telemetry events for each of those 5,000 scooters and streaming that into Kafka. So now that we've connected to Kafka, it's pulled down a preview of what our data looks like. So you can see we've got some battery percentage and an ID for a journey if the scooter is in use. We've got its lat and long, and et cetera, et cetera. So that's pulled that data from Kafka. It's analyzed it. It's determined what our column names are. It's tried to work out what the types are. If we wanted to adjust the column names, we can. If we want to adjust the types, we can. I'm going to leave them as they are for now. I'm going to give that a name, which is, what shall I call it? Scooter telem. Scooter telem events. That'll do. I'm going to leave that and create. So now that we've created the data source, that is the managed connector to Kafka and the table that is going to write that data in. So you can see it's already connected to Kafka and it started ingesting our fresh data. So as we start streaming that data in real time, that's going to pull that out of Kafka and write it into Tinybird. Cool. So that is Kafka integrated already. So that's our first data source. And now I'm going to kick it over to Cameron, who's going to bring in S3.
I'm actually going to wait to bring in S3 because the first thing that I want to do, I'm going to build an API over this Kafka topic here. And you can actually see, so we're at 4 million rows in Tinybird now. This will continue to kind of trend up as Alistair continues to stream. But before we do that, I'll just show you, this is like a very bare bones retool app that I've built. And actually, I'll just go into the editor view here. And basically what I've done right now, all this is, I've got a little Mapbox map and I have this little button that sort of simulates like getting a user location. So if I click this, you'll basically see, and actually I'm gonna add a little zoom here to the map. Let's go to 12. There we go. I'm going to zoom in for you guys a little bit so y'all can see. But then if I get a location, it's going to kind of pop me around the map. It's basically just generating a random Latin long within the Las Vegas city limits. So you can see that we have this kind of idea of generating a user latitude and longitude. I store those as variables in Retool. You can see those right up here. So let's switch over to Tinybird. And what I'm going to do is from this data source, I'm going to create a pipe. And what I want to do is basically my first APIs. I'm going to name this nearest available scooters. So basically, if I'm a user in the app, I want to see which scooters next to me are the nearest available scooters. The first thing that I need to do is, because we're streaming in all of these events, I need to get kind of the latest state. It's kind of a deduplication on that stream. So I'm going to just call this first node. And actually back up here. Tinybird pipes is basically just, you can think of it almost like a Jupyter notebook, but it's basically just a way to write SQL in Tinybird. And so instead of writing everything in one kind of big lumpy query, you can break it up into these nodes, and then Tinybird will actually kind of construct the final query based on those nodes. I mean, the nice thing about this too is, like, as we build nodes, this one I'm going to build here will be 3. You can actually see the performance of each node and kind of analyze that. So actually not get latest nodes, get latest events. So what I'm going to do is just select star from scooter to events, and then I want to order by timestamp descending, and then limit 1 by scooter ID. So basically all I'm doing here is I'm getting the last value for every scooter. So just kind of doing this deduplication. And you can see this this warning here that Tinybird's giving me, which is, hey, this is scanning the full table. Right now, it's 214 megabytes. That's not great, but it's not terrible. But I'm processing about I'm processing almost 700 megabytes of data to run this query. So in a bit, Alistair is going to optimize this for us, but I just want you to see that, hey, this is not the best SQL, but we're going to roll with it for now. And then what I want to do to get the latest available, the nearest scooters, is I'll get the scooter ID, the latitude, and the longitude from this latest events. And what I want to do is say, well, where status equals available, right? Goodness. And so, okay, so these are the scooters that are currently available. And you can kind of just see like, okay, I'm going to get, um, yeah, I'm getting the latest for each scooter, the latest one that's available.
Just to
And then
point
the
something
last
out
thing,
in that
yeah, yeah, yeah,
query is if you look at the from, you can see that
yep,
Cameron is querying the node that he had just created previously. So that the first node that he created, which filters the data to only get the latest events, he called get latest
yeah, right there.
events. And in the from, in that second query, he's actually querying the result of that first node. So you can just start to chain queries down. And that's what he was talking about when you can break queries down.
Yeah, and you got this nice little thing in the UI where you can actually check out the schema of each data source in each node. It makes it a little easier to query. So actually, I'm just going to call this available scooters, and okay, and then the last thing I'm going to do is I'm going to calculate a distance because that's ultimately what I want to do. So I want to get actually, I'll just do select star because we don't need all that, and then we're going to calculate a distance now. I'm not going to use real distance math just for the sake of simplicity. I'm going to do kind of a, square root of the sum of squares differences between the latitude of each scooter and kind of a user defined latitude. And so what I'm actually going to do here is pass a query parameter, and you'll see how I integrate that with Retool. And I'll just put this somewhere as a default. So what I'm doing here in these curly braces is I'm basically saying when we publish this as an API, this value, this query parameter, user latitude, is a type float 32. It can be passed to the API, and the default value, if it's not passed, would be 36.08. So I'm going to raise this. Let's see, where do I want to put that? Right here. Put that in the power, and then I'm going to add power. Let's see, same thing here, longitude minus, and we'll do the same thing, float 32, user longitude, and for a default value, I'll do something like minus 115.3, and so there we go. We raise that to the power of 2 as well, and make sure that that is all good. And I'm going to call this distance. And then what I want to do is order by distance ascending. So that'll give me the nearest scooters, and I'm just going to get the latest 10 results. And there we go. Okay, so I've got 10 results here, and kind of this pseudo distance value. And so what I'm going to do is turn this into an API, and I'll just name this last node endpoint just to help me navigate. And then I just come over here, click the node, create API endpoint, and I get a little bit of confetti because I now have an API endpoint. And you can actually see we get some sample usage down here. You can see our parameters, our query parameters, and then we've got some observability metrics here on this API. So I'm going to copy this sample usage, and I'm going to shift over to Retool. And what I'm going to do in Retool is I'm going to create a resource query, and I'm going to call this nearest scooters. And I want this to be a REST query. And I'm going to paste that in, and you'll see if I run it, I'm getting this JSON output from Tinybird. So this is hitting that Tinybird API. Now, what I want to do is change these hard-coded defaults to these values in Retool. And so I'm actually going to use this user lat. I'm going to get this Retool variable and do the same thing for longitude.
And just for clarity, the thing is that this is a standard REST API that it's published, right? So if you weren't using Retool and you were using any other app builder, you were building a custom web app, or you were building a mobile app, or whatever you were building, anything that can talk HTTP can hit these APIs, right, and run those queries. There's no like client libraries or like integrations you need. It's just standard HTTP. Do a GET request, get result.
Right. So you can see, like, if you were going to request this in JavaScript, like, it's basically, it's a very simple fetch, right? So very, very basic stuff. Okay, let's go back over to retool. And okay, so this is working. And now what I'm going to do is on this map, I'm going to say that the points, I want them to be this nearest scooters API and get the JSON from that. And there we go. I've got the 10 nearest scooters to me, and this is actually populating from the Tinybird API. And actually, just kind of to make this a little more real-timey, I'm going to go into retool and I'm going to make this run every 5,000 milliseconds. So as these scooters, you can see that it updated there. As these scooters move around, as people are using them, as they become available in use, things like that. So you can see how that's dynamically changing based on this stream of telemetry events that we're getting from Confluent. And then what I would also want to do is maybe give the user some controls over how many scooters that they see, and maybe like, hey, if I want a scooter that has a certain battery percentage, I want some control over that. I don't want to get a scooter that's only got 20% battery. So I'm going to add a couple of components here in retool, some sliders, and this first one, I will call this. I'm going to just call this battery threshold, and I'll say that a user wants to have by default a scooter with at least 60% battery, right? I'll just name that battery, and then what I'm going to go back and do in my Tinybird API, and so go this available scooters where I'm filtering, and I'll add here, right up here, and I'm just going to add, and we'll call this will be well, I guess it's a float, and we'll just call this battery threshold 60, and let's see, and battery percent is greater than or equal to, so I'm adding another query parameter here. So I'm going to say I only want to show scooters with a battery threshold of at least 60%. And then I'm also going to change this limit, right? So if I want a user to be able to, just call this results, we'll set a default of 10, and I'm just going to drop this for simplicity right now. And so that will allow me to sort of dynamically pass a limit. So switching back over to retool, stretch out the slider. And what I can go into this, back into my nearest scooters API here and add these query parameters. So we had a battery threshold, and I'm going to call it battery threshold.value. So I'm going to pass that to the API, and the same thing, I called it results. And I'm going to, well, I need to add a slider here. So let's wait on this one. We'll run that. And just so you can see how this battery threshold is working. So as I increase this battery threshold, the scooters are getting further and further away because there are fewer scooters that have, a healthy battery. If I bring this way down, oh, hey, all these scooters are really close because there's a lot of scooters with a low battery. And then let's just duplicate this. And
so while you add that slider, there's one caveat to the data generator that is basically the battery percentage is only decaying.
our scooters are going to run that. We're against the clock here.
What our scooter company has not yet done is employ some engineers to actually go around and charge any of these scooters.
That's right.
So that is one limitation that goes. So the longer this stream goes, the more scooters that are going to run out of battery completely.
We're still raising funding to hire those engineers. Go to our, whatever. Never mind.
Really, what it is they can't find any other scooters because we've not built the business app for them to actually go and locate any other scooters with that battery. Right. So we got.
That's right. So, okay. So now I have this dynamic limit. As I change this, it's going to change that. Well, what did I mess up here? Did I get this right? Did I forget to run that? Oh, not limit. Results was the name of that query parameter. Okay, let's try that again. There we go. Okay, so you can see as I slide this, it's going to show me. So if all I want is the nearest scooter to me, boom, there you go. So we're just dynamically making a request to that Tinybird API. Okay, so going back to this API, let's take a look at these stats. And actually, I mean, this is very not great, right? I'm processing almost a half gigabyte, and it's only going up as more data streams in, and this is taking half a second to respond, which is very suboptimal. And so I'm going to kick it back over to Alistair, my trusty data engineer, to optimize this pipeline with a materialized view. So let me do that. I'm going to add you back, Alistair.
Cool. Yeah. So I'm on the same screen that Cameron was just on. And what he's done in the past 5 minutes is we've gone all the way from absolutely nothing through to building our ingestion pipelines of getting our streaming data in, writing the query to do the analytics, publishing an API, and building a front end application to actually do something with it, right? So in the past 5 minutes, we've actually managed to accomplish quite a lot, and like prove the value of our use case effectively. But now that we've proven it, once you actually want to get it into production, we can already see some red flags on the metrics of this, right? So as Cameron was saying, the average process data per API request is 400, 500 meg. So not fantastic. And the average latency is 530 milliseconds, which, actually, if you were building a 5-minute POC and you had put literally no care at all into like optimization, it's not terrible, right? But there's no reason it can't be better. And yeah, if you look at the trend, it's only going to go up. And the reason that's happening is because we're doing a full scan query over the raw event table every time that API is hit. And because we are streaming data into that table is only increasing. So every time we ingest some data, every time we hit the API, it's going to keep going up and up and up and up and get worse. So really all we need to do to serve this this use case is query the latest events that have come through. We don't need to query the entire table, which basically means we want a table with 5,000 rows in it, because we've got 5,000 scooters. They're sending the latest events. We just want the latest 5,000. And the way we're going to do that is with a materialized view, right? And materialized views work a little differently in Tinybird than in sort of other legacy systems. So I'm going to show you how that works. While I do that and type that up, Cameron, why don't you take us through a brief how materialized views work while I type, so that we're not just
sure. Yeah, I remember I'm the full stack engineer here, so I'm a little above my pay grade, but no. Yeah, so materialized views. So the way that you define that in Tinybird is you just create a pipe like you normally would, and you define an SQL transformation. And what you'll notice here is, like, on the API that we were showing, we're doing all of that processing, all of that deduplication at query time. So that's not only expensive computationally, but it can be expensive in terms of money. You don't want to process all of that data, especially if you have many thousands of users making concurrent requests. And so what materialized views do in Tinybird is you basically define a materialized view in a pipe, create a transformation, and then instead of publishing that transformation as an API, you create a new data source, and that data source is a materialized view. And what is going to happen is, as new data streams in, those transformations will actually get calculated incrementally in real time as new data arrives, and materialized in that materialized view. And basically, the optimization here is that instead of doing all of that processing at query time, we're going to do it at ingestion time. So basically, instead of doing it every time a user makes a request, we're going to do it once when the data is created. And there's some nuance here, just around these materialized views. So Tinybird is built on top of ClickHouse. This is OLAP database, and the materialization process kind of happens in the background, and the results occasionally get merged. And so we'll have to do a final deduplication in our query. But the nice thing is that instead of querying 4 million rows and counting, we'll end up querying, if we hit this materialized view, we'll end up querying something like 5,000 rows plus any final results that haven't been merged. 5,000 because we have 5,000 scooters, and so it'll really reduce our cost here. And of course, if you have more questions about materialized views, you can ask them here. We have a lot of documentation on those as well. But they're really powerful optimization for us in Tinybird. And it looks like you've finished your SQL
just in time.
Yeah.
So the query that I've written here for my materialization should be very familiar to what Cameron wrote earlier when he built his original use case, which was, in his first node, he was doing this order by timestamp and limit by 1 to get the latest. All we basically want to do is just materialize the results of that, so you don't have to do it every time an API request comes in. So what I've also done is statically select the columns that I want to materialize, because when you bring data in from Kafka, it can also bring in all of the meta fields, and it's up to you whether you want to use those or not. But for this use case, I don't need them, so I'm going to get rid of them because then it's less data to scan. So the trick here is, I've written this query and now I actually want to turn it into a materialized view. So I'm going to hit, again, this little action button, and instead of create API endpoint, I'm going to do create materialized view. And that's going to give me some options to fill out. Now, I'm going to call this scooter tilem events latest. You can pick your sorting keys and your partition keys and everything as you would with a standard data source. But what I want to do for this is I actually want to use a special engine for a materialized view, which is called the replacing merge tree. And the replacing merge tree effectively means that we can take a key that gives us some uniqueness. So in our case, a scooter ID identifies a unique scooter. And then we can say, we can give it a key for a version and say, for each of these keys, only maintain the latest version defined by whatever this version key is. So if the sorting key for us is the scooter ID, which is our uniqueness check, and then we've got our engine, we give that the timestamp. Basically, what that means is for every scooter ID, I only want to maintain the state of the latest timestamp, right? So imagine you've got your table and you've got 1 million rows in there, and for scooter ID 1, you've got timestamp 3 seconds ago. You ingest a new one for scooter 1, and it's got timestamp of now. It's going to say, hey, I've got an existing state for this scooter. I've just seen a new event for it. Bring in that new one because the timestamp is later.
Alistair, don't forget to actually update the engine replacing merge tree.
That would be a bit of a disaster, wouldn't it? So now the nuance of that is kind of what Cameron was getting to with materialized views, in that the way that replacing merge trees do the eviction of the previous state happens in a similar way. It's a background process, and you can think of it sort of like lazy eviction. So when a new row comes in and it sees that there's a previous state for it, it's not saying, evict the previous state and bring in the new state. And so you've only ever got one state. What it's doing is bringing in the new state and leaving the old state there. And then a background process is going and evicting all of the old states. So, you eventually you get rid of those old states, which means you do start to reduce the amount of rows you have over time. But at the point of query, you can't guarantee that when the last eviction happens. You don't actually know how many copies of the data you've got. You've definitely got less than your raw data, but you might not only have one copy. So you do have to do the eviction or the deduplication again at query time, but it will always be less than what it would have been otherwise. So I always find, by the way, that is a much easier concept to explain with a diagram. It's very hard to do conceptually without one. So I'm going to hit next, and I'm going to ask it to take all of the previous data and all of the new data and go and hydrate that materialized view. So I'm going to hit that, and that's going to go away and do that. So there was a question there that came in saying, is the MV being updated in real time as new events come in? Yes. So they are incrementally computed at ingestion time. So as a new event comes in, it is triggering the materialization process to say, hey, I need to rerun and incrementally update my end state materialized view. And it only affects the states that are actually impacted by the new row coming in. So if there is a state in there that's talking about, other stuff, it's not going to go and change any of that state. It doesn't need to recompute that. So significantly more efficient than traditional materialized views, which run on a schedule and then go and recompute everything every time. So we've got a materialized view, and that's using the replacing merge tree to try and deduplicate stuff. So what we should end up with is basically another data source, which is now called security events latest, which should have significantly fewer active rows than our raw data source. It might not have only 5,000, but it's probably going to have near that. It might have 10,000, 15,000, 20,000, but those will keep going down to 5,000 over time. Now, if you look at the original query, Cameron had in this deduplication here. And so what you could do is at the start of this query, change this to query that materialized view, and that would work. And that would always return 5,000, and it would be significantly less than doing it over the raw table. But if you wanted to go and add more pipes, so more use cases, more APIs, and you always wanted to have this at the start because you always only want to talk to the latest, you don't want to have to really go and remember to do this every time and rewrite it. So what we can do instead is I'm going to be lazy and just copy and paste that and add a new pipe whose pure function is just to get those latest ones and do the deduplication. So I'm going to call this pipe get latest events. Paste that in. Did I not copy and paste? It would help if I right buttons and copy and paste. Paste that in. And I'm just going to contain that logic within this pipe as if it was a kind of UDF style lambda. And I'll call that endpoint, and I'll publish that as an API. And so if you wanted to hit that as a REST API and just get the latest 5,000, you could. But what I'm going to do is actually use that pipe in another pipe. So I'm going to chain them together. And I'm going to change this get latest events node, which is part of Cameron's original pipe. And I'm just going to do select star from get latest events pipe. And so what have I broken there?
Did you? Weird.
I'm sure I am missing something very obvious.
From? How about a from?
I said it would be obvious.
It's always the stupid stuff.
So yeah. So now instead of having to write that logic every time at the start of my pipes, I can just select star from that other pipe, and that's going to go and do that deduplication for me. Yeah, thanks everyone in the chat that's pointing out that an idiot and didn't see the problem. So that's going to do that for me and just make that logic super simple. So now basically what I've got there is an optimal way of filtering that data. And now when Cameron ever wants to go and build a new pipe, he doesn't need to think about that optimization. He can just use that as a standard in every pipe and do a select star from get latest events pipe, and it will already be optimized for him. So if we go and look at his metrics for this again, you can actually already start to see it changing. So his retool app is refreshing every 5 seconds, and we can actually see those requests coming in. So the amount of requests at the top here hasn't changed, right? Every 5 seconds, you see one request come in, right? And you can see the spike in process data every time one of those requests came in with our unoptimized one. But now those requests are still coming in, but the process data has just dropped. It's flatlined because it is now tiny. So if I try and take this to 1 minute, you can actually see now that all of those requests that have come in since we did the optimization are processing 1 megabyte per request rather than 500 megabyte. So orders of magnitude less. And the average latency is now 20 milliseconds, right, rather than half a second. So, 5 minutes to do that very quick optimization with very little impact on our application developer. And we have, dramatically improve the performance, and it's pretty much like production ready now for you to take away and go and build some more stuff.
Yeah, that's pretty cool. We did have a question about being able to export. Will I be able to export all the data to a CSD or CSV or NDJSON from a data source or materialized view? Go ahead.
So yeah, so yes. So one of the nice things about your APIs as well, right, is if I go to your API, is it's not just like a JSON response that you can integrate with your apps. So what you can do is every single API is actually also published as CSV and NDJSON and Parquet. So just by changing the .json in the URL, you can turn that to .csv, and it will export a CSV file. You can download that. So to go and export all of your data as a CSV, you can write an API that is select star from my data source, publish it as an API, and go and hit the CSV URL and download it as a file. And then that's not just for you to go and download it. You can use that to go and integrate it with other systems that want to hit an API and get a CSV. And like Parquet is pretty useful if you want to build real-time apps over Tinybird and then integrate it into a, say, data lakehouse pattern. You can expose the Parquet files, have something hit the Parquet URL, write those into S3, and you've got a way to integrate with a lakehouse in S3. There was another question: is it possible to find an index on columns within a node? So the best way to optimize with like indexes in mind is sorting keys, which are defined on data sources. So whenever we brought our data in from Kafka, we can define what the sorting keys are for that data source to order the data as it's ingested, and then our pipes just query that and get the benefits of those sorting keys. I think that covers that.
Yeah.
Question, and then another one came in.
Yep. Yeah, a question about, is there a limit on the rows you could export via API? I know that there is a limit.
Yes.
I don't remember what it is.
So there's a limit of 100 meg on the response of any API request. So if you've got more than 100 meg returned by your query, so you're doing a select star on your data source and it returns more than 100 meg, it will cap you at 100 meg. So the way to get around it is to do pagination, right? So you can say export this many rows, which comes below 100 meg, and then just give it the parameters of the pagination to get then the next chunk and the next chunk until you've caught up. And then if if you want to keep doing it and so that you keep up with your data source, then just hit the API more frequently and do smaller exports with a timestamp to say, hey, select star from the previous timestamp, and do that more frequently to get smaller chunks, and just keep doing that. We can actually adjust those limits as well. So if you do find yourself hitting those limits and you need to go above them for particular use cases, we can adjust them. They're not hard limits. So come and chat to us if you have a use case that goes above that. So I'm going to pause the questions for the second and go back to you, Cameron, so you can finish off the last bits.
Yeah. So let me share my screen here. And so I've actually I've made a change to Alistair's get latest pipes, and what you can see is that I've added this this little logic here. It basically says, hey, if a scooter ID is passed, then I want to filter these results by that past scooter ID. So the idea here is that this latest events pipe, we could limit it to a single scooter. In theory, you could actually even do like an array here. So if I wanted to limit it by a group of scooters, I could. But by using this logic to say, hey, if you can just hit the endpoint without passing the query parameter, you'll get all 5,000 scooters. But if you just want one, you can do that as well. And that's going to benefit me here in a second. So if we go back to my retool app, you'll see like, okay, I've got these scooters. I'm going to move around so you can just kind of see how that repopulates. But clicking on them doesn't do anything. And I want to be able to sort of get information about that scooter. And so I'm going to create an API to get that information. But my scooter stuff, my scooter dimensions are stored in this S3 bucket. And actually, I've got this, I've just caught this little S3 bucket, Tiny Bird scooters, and I've got this file in here that contains kind of the make and model and all this information for the scooters. And so I'm going to bring that data into Tinybird by creating a new data source, choosing Amazon S3, and then I'm going to copy over my stuff here, my access key and my secret for this bucket. And then this one is in US East 1. And I'm going to connect to this bucket. And this should happen pretty quickly. There we go. And I'm just going to call this connection, we'll call this Tinybird Scooters S3. And then what I can do here is basically define a path expression to this bucket for the files that I want. And so I'm just going to do something like Tinybird Scooters and just star.csv. And so that should give me, it would give me every CSV file in my bucket. I only have one CSV file in my bucket. So we'll see that show up here. And you'll see this tag as a schema reference. So when we have multiple files, what Tinybird will do is kind of choose one file to say, okay, I'm going to analyze the contents of this data and define my schema there. So click next. And with S3, what we can do is we can actually, we can tell Tinybird to continually update and append data as new files are added. I'm not going to be adding any files, so I'm just going to do this once. And so we'll let this kind of, what it's going to do is it's analyzing that file and it's pulling in that data. And so I'm just going to call this scooter info. I'm not going to worry about changing the schema right now because these are the three columns I'm going to use. They're all strings. That's great. And then I'm going to create that data source.
Yeah. So the nice thing here, right, is the patterns you could do. So we just spoke a second ago because of that question of integrating it with the lakehouse pattern, right? Of if you want to use Tinybird before your lakehouse and push in to hydrate your lakehouse, that's a pattern you can do. But also if you've got data that's coming from another source and it's just being written as files into S3 because it's slowly changing dimensions, and you would just want to use it for lookups, you can do that model as well and bring that in to then use that to join with streams for enrichment of your events as they come in.
Yep. Okay. And so I'm going to create another pipe here. I'm going to call this get scooter info. And I'll just do, so the first thing I'm going to do is do that, that deduplication. So we're going to select star from, what do we call that? Get latest events pipe. There we go. And I'm going to, and I'm going to go ahead and do this filter, right? Where scooter ID is equal to string scooter ID. So I can pass a scooter ID to this, and I'm just going to pop a, well, we don't have, that's not a big deal. What I do, select star. My from is there, right?
I think you're missing an equals sign this time.
Oh, yep. Scooter ID equals. There you go. Okay. So we'll call this get latest, and then I'm going to basically hydrate my stream data with these columns in. Well, let's do select star from get latest, and then we're going to join this on my scooter info table using scooter ID. Just using scooter.
I'm pretty happy that you've made a basic SQL error now after my from debacle. After you you managed to get through that whole lat long math thing without making it a typo, and I thought that was quite impressive.
that I'm gonna have to copy and paste that in a little bit. So I'm just getting what I want to get here is the battery percentage. We get the status of it, and yeah, that should be good. And since I'm not actually passing a, well, let's see. Let's just kind of copy a known scooter ID here. Set it as a default so we can see this right here. Okay, we got a scooter, and then we're gonna hydrate. Okay, cool. So this scooter is called the Lemon Drop 1000. It's got 24% battery, and it's currently available. So I'm gonna publish this as an endpoint and do it from up here for fun. And then great, I'm going to copy that, switch back over to retool. I'll just duplicate this query, but I'm going to call this scooter info. paste
And
that in here.
we are probably going to find now that a lot of those batteries have decayed to
Yeah,
20%.
that's fine. So this little map is called scooter map. And so what I want to do is say when I'm going to create a little interaction here. So on point select, I want to run this scooter info query, and I'm going to pass the scooter map dot, the selected point, and then I'm going to pass that scooter ID, which is coming from that TinyBird API. And so now if I go over to, well, I guess I need to create some components here. So we'll just quickly drop some text. This will be, we'll do make, and then we'll do scooter info dot data. We'll get the first result and scooter make. There we go. It's a lemon. I'm going to duplicate this. We'll get model, same thing. Cool, pi 2000, and then I'll just do a little progress bar for the battery, and I'm going to do value will be the same thing. Scooter info, go through that JSON, battery percent, and there we go. And I could even dynamically color this if I want, but I don't really have time for that, so I'm not going to do it. So now, if I click on a scooter, that data is going to change. So now I'm getting the individual information for, let me zoom in here, for each particular scooter. So the last thing, I've got 8 minutes. I'm going to see if I can pull this off. I'm not showing a price, right? And what I might want to do as a business is dynamically price the rental of these scooters, based on how many are available or how far it is from the user, right? If it's like really close and it's got a great battery and there's only one scooter available, then hey, you're going to pay a premium. That's probably a bad business choice, but for the sake of this use case, we're gonna try it. And so what I'm going to do is create another pipe, and we'll just call this get scooter price, and going to do that same. I'm just going to copy this over because I want to do that same deduplication. And then what I will do is I'm going to get the battery percent. Select from, let me call this get latest again, and select from get latest. There we go. So select battery percent, and then I'm going to copy and paste that distance calc that I did earlier. So from get latest, what I do? Oh, I didn't. Guess I didn't copy that whole line there. There we go. Okay, so now for each scooter, I have a battery percent and a distance from the user, and then I'm just going to copy and paste this for the sake of time. I'm at another node that's going to do some pricing logic here. And so what this is doing is it's saying, okay, return the distance because I might want to show that in my app. And then I've got a base price of $5. I've actually made this a query parameter in case that would change for some reason. You could add a surge multiplier. If that's defined, I'm actually just gonna we'll set the default of 1, which is basically saying, hey, like if we want to initiate surge pricing, that would actually do a multiplier. And then I'm adding some very basic logic here, which is like, okay, if the distance is less than 0.05, multiply the price by 1.3 and descending down. And then the same thing with the battery percent. Like if it's greater than 80, multiply the price a little bit. If it's less than 20, then actually they get a discount. And so I didn't call that get distance, did I? Here, get distance. There we go. Now I've got this price for this scooter, and so I'm going to just publish this as an endpoint really fast. Copy it over. Go back over to Retool. And I'm just going to, let's duplicate this. We'll call it scooter price. Paste that in there. And then, Yeah, search. So you can see those query parameters get populated. Again, this is going to be based on the user's location. And so I'm passing those app values in there. And then the scooter ID is the same thing. I want to do that scooter map select point dot scooter ID. And so now let's go over and drop another component in here. Actually, I'll just duplicate this, pull it down, and make this a little price, scooter price dot, go through that JSON dot price, and there we go. So you can see now as I kind of click on these different scooters, depending on, let's see, I'm having trouble clicking here. Here, let's get a little higher battery percentage. So they go, there we go. They spread out a little bit. Trying to find one that has a battery percentage less than, they're all 24. Al, what'd you do? Anyways, I'm trying.
So this is some bad logic in my data generator, but because all the batteries are decaying, there's some logic in the generator that says to stop renting them out once they get to a low battery, because then a service person should go and charge them. But we never implemented the go and charge them.
Let me see. I just want to find one that's like a little further away to see if that dynamic price will change. Oh goodness. I guess not. I guess they're all close enough. Anyways, this would update based on that API. You could actually see, like, in that TinyBird API, that particular scooter that I was querying had a price of 5.5 because of the way that logic was breaking out. So, the basic idea there is, hey, we've added some dynamic pricing to these scooters based on, their distance and their battery and things like that. And I think we're out of time. We were going to kind of do some scooter stuff, some, the company side of things. But actually, if you check out the GitHub repository, there's some code for that in there, some pipes for some of that. But yeah, if there are any more questions, we will take them now. Otherwise, we'll wrap up.
Yeah, and I mean we'll keep updating that GitHub repo, and we'll fix my my battery decay problem, but we'll also expand on that business, right? Because part of what we wanted to show is not just, hey, building the consumer application of, user has it on their phone, go and find a scooter, but also actually your internal application of, you've got engineers driving around the city who need to go and fix scooters that are broken or out of battery, and they need an app to be able to say, hey, look, I'm on this street, find me a bike nearby that I need to go and service. So it's pretty flexible, but it doesn't look like we're getting too many more questions come in at the moment.
I don't think so. I think I think we'll wrap it up. Like I said, you'll get a follow-up email in about 30 minutes with the recording for this, the link to that repo, and then a kind of a guide that we wrote on building these kind of analytics over Confluent specifically. We're kind of we go hand in hand a lot with Confluent because it's just this great approach to sort of, very similar value prop of, hey, I don't want to mess with all this stuff. I don't want to mess with all this infrastructure. I just want to build, and Confluent and TinyBird kind of share that value. So cool. Thank you, everybody. We'll see you next time.
Thanks, everyone.